Okay, good.
Hopefully.
I don't know what
Yep.
to do. Oh.
All right, go ahead.
Okay, so it's Mathematics of Counter-Strike Global Offensive, and that's obviously by William Julius and
Todd Sweeney.
okay, and the history of Counter-Strike. It was a game first released by Min Lee and Jess Cliff in 1999 as a gameplay modification for Half-Life, which was produced by the Valve Corporation. And then the Valve Corporation quickly purchased the rights to make this into their own franchise, and then they've produced 3 major titles since then. We see the original Counter-Strike, Counter-Strike Source, which was released in 2005, and then Counter-Strike Global Offensive, which was released in 2013.
Actually, it's 12.
Was it 12?
Yes.
Oh wait, actually I have that on there. It's 2004. I was a year off. Okay.
Oh, and then also, if you're wondering what the heck a mod is, as previously stated in that game, it's where you take an existing game, as was mentioned, Half-Life, and then you modify the game files to create a so-called new game or change it up. And let's see. You already said that, didn't you?
Yeah.
And yeah, it's a very popular game, close to 3 million unique players every month. So in classic competitive Counter-Strike, there's 10 players and they're divided into 2 teams, evenly of 5 players each. One team represents the terrorists and one is the counter-terrorists.
The terrorist goal is generally to do something evil, you know. And the counter-terrorist is to stop the terrorists. And then, yeah, we have
Here are some pictures of various factions because they look different depending on the map you're on.
those are the ones on the map we're focusing on today. And more pictures and gameplay continued. So there are 2 main game types in competitive Counter-Strike. We have defuse, where the terrorists attempt to plant a bomb to destroy something. Usually it's something like food for orphan children, something evil. Then hostage, where the terrorists attempt to defend 2 hostages for 2 minutes while the counter-terrorists attempt to rescue them. We're focusing on defuse because that's the map we picked. It's a defuse map, and then it's Dust 2.
And here's Dust 2. It's one of, or if not the most popular map there is in Counter-Strike right now. And it's a defuse map, so the T's are trying to plant a bomb while the counter-terrorists are trying to stop them or defuse it if it is planted. And today we're going to be examining spawning and the time it takes to get to key locations on the map, and also main physics. That'll be later.
Yeah, spawning, just because I'm going to assume, Mr. Crew, you probably don't know what that means. It's
Correct.
On the next
is
slide.
how players are placed at the start of each round. So players at the start of each round are placed in these little green zones right there and right there.
Where?
These little green boxes.
Oh, okay.
Right where it
Right
says
there,
team
and they're
spawn.
placed pseudo-randomly in there. It can't be completely random because it's a computer thing. Yeah, so.
That's what it explains right there.
And then the green boxes are the spawn zones.
And to find the time to get to these key locations, we decided to break it up into first the time it took to get out of the spawn. So we used the distance formula based on where you spawn and where the point of exit was to get out, and generalize the time it take to get out of spawn to the corner.
Yep, and this is a picture of T-Spawn. It's a lovely neighborhood. You can see ramp, ledge. This is T-Spawn. You can see a box, a
CG.
door, a CG, yeah, box to door. Yep. And here's a video showing traveling to the key locations we
Did you
picked on the
turn it
map.
on from there?
What?
Did you turn it on from there? Because that'd be the sweetest thing ever.
Yeah, I can.
No?
Okay, it's actually pretty good. So yeah, this is going to various parts of the map.
How do you click on this thing?
Just click.
I think you just click.
Just push it. Just push it.
What do you click?
Click just.
Oh!
Okay, yeah, so here is going from CT spawn to long A. Yeah, long A.
Yep.
See the corner peak there? Is going from CT spawn to B tunnels. Todd randomly jumping.
I had fun.
And it's CT spawn to catwalk, and you notice with catwalk you have to actually go all the way up around so you can get back to the same spot you were. It's just above it. You can't jump up. So that's catwalk from CT spawn. From T spawn to long A. Just through those doors, and you actually get to see right where we were before when we looked at long A. From CT or T spawn to
Cat.
Todd looking at this stuff again. To a catwalk. It's actually right here, you're right above CT spawn, so. And then from T spawn to B tunnels. I don't think you have to stop it. I think I
Yeah,
can
sit
see
on this
next
next
one.
one. It's embedded in G. Yeah,
Or not.
it's not.
Code that it's written out. There we go. Okay, so yeah, here's our map, and these are just the routes drawn on the map. So we see from CG spawn to B-tons, G spawn to B-tons. See from G spawn to catwalk. You see from CG spawn to catwalk, and you can see the really long route you have to take to get right above you. You see from T spawn to long A and CG spawn to long A. You see that you don't actually have to get to like where the arrows meet, but you can see across there, so we consider that a conflict point because as soon as the players can see each other, that would be when conflict actually starts to happen.
And here is our way of generalizing spawning. So let the spawn zone be the whole green rectangle there, and then that spawning base is the position that a player spawned in at. And those corners right there are the most common points to leave spawn at.
So we want to find the distance.
So yeah, we want to find the distance to go to those places. Then from that, we can get the time needed.
Yeah.
Here's our distance formula. So for your x2s and y2
Hold
or
on.
your
We need to
ones.
explain the history.
Oh. I was jumping way.
So yeah, so this is a distance formula, and it basically describes how you can find the distance between any 2 points in a 2D plane. And it's based off of Pythagoras' Pythagorean theorem. Probably didn't call it Pythagorean theorem, probably called it his theorem for calculating the hypotenuse of a right triangle. So when you generalize spawning, we see that if we say that our player is at position x1, y1, and that we're heading towards their position x2, y2, we can then use our distance formula to calculate that distance. But we need to modify it a little bit, and you can explain to me.
So here we just have the normal distance formula, which makes sense for the x1 or the x2, one or the other for your player's position, and then the other one for being the corner that they're trying to reach. And then the divided by 250 is to get the time it would take to go to that point, because we calculated that the player has a velocity of 250 units. Oh yeah, by the way, all these units are the in-game units they use, no actual specific one.
Because of how the game calculates units, there's no steady translation between units and feet or units and inches or anything, because players are measured in units, which translate into a foot value, and then the map is measured in units, which translate into a different foot value. So the players and the map actually exist on different scales, and it's weird. We tried to get it to equal out some sort of feet measurement, but we couldn't because of the differences.
And also, so really it just simplifies down to distance divided by velocity, which is time.
And to get that 250 value, this is actually the only value we had we didn't have to calculate, because this is the only one we could actually find in the game console configuration. So it's 250 units per second.
And this only gives us the time coming out of the spawn zone, because we want it all the way to the key locations. But then, since we have the time needed to get to those corners of the spawn, you can just really add on a constant going to those various locations.
And then we did the timings, and that would be our total distance formula. So we see that we have our distance formula here over our velocity, plus the time it takes to get to the edge of spawn to the locations. And we had timings that Todd so graciously did by videoing himself and then timing the videos.
And here's an example of a player spawning in at position 100, 200, and they're trying to exit out of the corner that's located at 0344.
Yeah, so this would be from
And those are the
T-spawn.
actual dimensions of T-spawn.
So we'd be going from T-spawn to
To B-tons.
B-tons. Yep. So yeah.
And you plug those points into your equation, and also you add the constant, which from getting to that corner to B-tons from T-spawn, as if they're 11.067, and then you add those all together, and then you get a total of 11.768 seconds to get there, based on that spawn.
We also, and you can go click on these if you want to, we figured that since we already made up we made up an equation to solve for this, we can also generalize this into a curve. So what we did was we actually made 6 different curves, which represent the time it takes from each of the spawns to the locations. And I'm probably not going to pull up all 6 of them because they all look fairly similar. But you can sort of see that as your X and your Y both increase and are at the maximum, the time is at a maximum, and then you can see your corners where, not rotating it.
I'm rotating it.
Can you rotate it a little bit more?
You
Okay,
It's the
perfect.
best corner.
You can see when your Y is at a maximum, it takes, it increases along there. You can see when your X is at a maximum, it increases along there as well. So, oh yeah, another thing we need to know, we did restrict our domain to the area of the spawn, so we don't have these super large solutions. So this is actually relative to spawn. If you scroll up, I think it has a maximum Z value, and Z
Yeah,
should
it's,
be
I
time.
have everything listed here.
Yeah, so if we look at our Z value, you can see that it will take a minimum of 11 seconds to reach that location, and it will take a maximum of 14 seconds. And do you want us to pull up more of the models, or?
No, this is, I like this.
Okay.
The only
Unless
thing
somebody
I
else
wish-
does, but right now, let's look at this. Maybe in questions, somebody
Okay.
wants to.
And then we go back to
The
the
other
page.
thing I wish we could do is, I wish there was a way, at least in that program right there, to overlay them, because then you could actually see the percentages and chances of beating the other teams at a certain key location.
Yeah, because you can see this
Based
whole
on where you
time.
spawn at, or where you do just assuming randomness.
Yeah, so what does this show us? It shows us, on a whole, CTs tend to have a lower average time, or lower average time to reach these locations. And this is because gameplay-wise, the CTs need to be able to get there before the Ts because they're defending objectives, not attacking them. We also see that under certain conditions, Ts can actually have a shorter time to reach those points. So there are conditions where if a T would spawn far away from the objective they're running to and T spawn close, the Ts can actually have an advantage getting those times before CTs can actually get there, or before CTs can actually set up the locations. And what this means is that if you have an entire team spawn on one side of the spawn zone, it can actually be beneficial to go to a particular area because you can get there before the other team may be able to and take the site before there's any strong opposition.
Okay, so now we're gonna move on to our next section, which is all about grenades. And they're very important, and there's two main grenades, there is more, but they're basically the smoke grenade and flash grenade. And they have a ton to do with physics, and I think that's all.
We need, well, we should point this out before we go on. It's in a video game, which means that we can't just use the 9.82 meters per second downward or meters per second downward as acceleration because they use all these custom values and stuff for gameplay reasons. So we actually had to derive a lot of this out. Yeah, another video.
This is the one showcasing the flash and smoke, isn't it?
I think so, yeah. So this demonstrates both types of grenades. This is a smoke grenade. You can see, it takes a second to deploy, and then it's all,
Oops. Oh, so much for trying to pull screen
just,
in.
yeah, just leave it as method.
Oops.
Click that. And so the smoke grenade deploys, and you see it makes it all smoky so you can't see through it. So you can block off the use of lots of angles, but it also hides your vision if you're inside of it. So you can use it to create temporary cover. And this is a flashbang grenade, and it makes you go blind temporarily and deaf. So that can be very useful if you're trying to take a site and you need an advantage as you're trying to push in.
And there's
So you need to click on the video. Okay, so basic principles is grenades move through the air, and their paths can be modeled by, well, their initial path as they're moving away from you can be modeled as a vector. And then since it can be modeled as a vector and you're in a three-dimensional plane, it can actually be broken down into three vectors, one representing the distance outward from you, one representing the distance upward, and one representing the distance left and right.
I think it's also worth noting that also in all of our examples today with vectors, we completely excluded one dimension just because it's really hard to represent a 3D model on a 2D coin like this. We've tried. Oh, so now what is a vector? It's really just magnitude and direction combined. And it was first used by astronomers to describe planetary motion.
And it's worth noting that these are Euclidean vectors, not other weird mathematical vectors that come up when you Google vectors. So yeah, so here's an example. So say we have little Billy, we'll call that little Billy. He's throwing a grenade. So we can break up the path of that grenade into the component outward and the component upward. And if we take the direction it goes outward and the direction it goes upwards, that'll give us our vector C. So we're basically breaking up our vector here into these two separate vectors there. So,
But now it gets a little more complicated if a grenade actually bounces off of something than that. So let the smiley face be a grenade and the giant straight up line, that will be a wall. So it's coming in at like that angle right there. And can you grab on? So it's coming in at an angle of A, and it actually will bounce off at the same angle, A.
Yep. And that is because when you throw a grenade against the wall, the force is then transferred back into the grenade, but only in one direction. So we see that when we have our vector, we can break it up into two separate vectors like we did before. But when we continue describing it, we can see that our B vector isn't changed by the impact and it continues to the side, while our A vector is reversed and applied back outward, meaning that this is the same, well, it's almost the same force back outward. It's not actually negative A exactly, because the game does model a little bit of frictive force when you hit the wall. So it would be a value slightly greater than A, because it would be